Non-parametric tests, much like the Bonferroni correction, from an application perspective, are not frequently encountered in the field. Again, like Bonferroni, I find these tests to be excessive exercises in academia, as they are most commonly brought up in committee meetings and by amateur researchers. Non-parametric tests are often misinterpreted both by those who utilize their application and by those who attempt to interpret results as readers. The whole existence of the non-parametric test vexes me in a way, as parametric tests were created specifically with robustness in mind. Unless you understand exactly what is happening under the hood as it pertains to non-parametric tests, I would recommend avoiding them, unless instructed to specifically utilize them otherwise. In my opinion, the confusion that they create is not worth the trouble. So in statistics, non-parametric tests are methods of statistical analysis that do not require a distribution to meet the required assumptions to be analyzed. Due to this reason, they are sometimes referred to as distribution-free tests. A non-parametric test is a method of analysis which is utilized to analyze sets of data which do not comply with a specific distribution type. As a result of such, this particular type of test is by design more robust. So it's even more robust than the parametric test. So we're going to talk primarily about the Wilcoxon signed rank test. And this test provides a non-parametric alternative to the one sample student's t-test, the two sample students t-test, and the paired students t-test. The test is named for Frank Wilcoxon, the chemist who initially derived it. And it's commonly shortened to the Wilcox signed rank test. And here are the hypothesis tests for each, the right-tailed, left-tailed, and two-tailed. So we're going to assume that you've already tested your data with the Shapiro-Wilks test and found it to be non-parametric. Now, if you need to understand what non-parametric data is versus parametric versus normally distributed data, there are lectures within this playlist that explain such, primarily the avian test lecture. But if you're already familiar with the concepts, we'll continue on. So this is a single sample Wilcox test, and you might recognize this example. The data for each one of these examples in CSV format is within the video description. A factory employee believes that cakes being produced within his factory are being manufactured with excess amounts of corn syrup, thus altering the taste. 10 cakes were sampled from the most recent batch and tested for corn syrup composition. Typically, each cake should comprise of 20% corn syrup. Utilizing a 95% confidence interval, can we assume that the new batch of cakes contain more than a 20% proportion of corn syrup? So our levels are below from the sample observations, and to the right, that is the data set. And again, it's in CSV format. If we're using RCommander, you're going to have to import the data into RCommander before proceeding if you want to work through any of these examples at home. So we have our data already imported, and we're going to go to non-parametric test within the statistics tab, and then we're going to go to single sample Wilcoxon test. And if it's a two-tailed test, we would select this option. Left-tailed, this option. Right-tailed, this option is indeed a right-tailed test because we're looking for greater than. Our null hypothesis is 0.20. That was given in the problem that we were looking at, the word problem. 20% is what we're comparing our samples against. And we just want a default type of test. So once all of this has been selected, click OK. Here is our output. As you can see, our null is 0.006386, which is less than our assumed alpha. We're working with an assumed alpha of 0.05, which means we're going to reject the null hypothesis. Because remember, if the p is low, the null must go. And in this case, our p is lower than our alpha value, so we're going to reject the null hypothesis. So therefore, we would state there was a significant increase of corn syrup in the most recent batch of the sampled cakes as compared to the historically sampled mean, p less than 0.01. Now we'll utilize a two-sample Wilcoxon test. In this case, a scientist creates a chemical which he believes changes the temperature of water. He applies this chemical to water and takes the following measurements. He then measures temperature in samples in which the chemical was not applied. So we have two distinct sample categories, one in which the chemical was applied and the other in which it was not. And each one is a separate observation. And I'm sorry that we're reusing these examples from prior example lectures, but here we are. Can the scientist conclude with a 95% confidence interval? 95% confidence interval means alpha of 0.05, that his chemical is in some way altering the temperature of water. So this is a two-sample Wilcoxon test. So we're going to go to the Statistics tab. We're going to select Non-Parametric tests, and we're going to select two-sample Wilcoxon test. Our groups are going to be water type. Our response variable is going to be water temp. It's going to be two-sided, so we're looking for a significant differentiation, not to see if the temperature went up significantly or down significantly. No, this is two-sided because we're interested in significance on either side. Type of test will be default, and with these particular options selected, go ahead and click OK. As you can see, our p-value rounded to two significant figures is 0.06. So in that case, if we're working with an alpha value of 0.05, we'll fail to reject the null hypothesis because our p-value is greater than our alpha value. And here is our data here. You can't get this to get in CSV format. Just go ahead and make this in Excel and import it into your RCommander if you wanted to test this on your own. So these are our hypothesis, the null and the alternative. The null is the chemical is not altering the temperature of water. That's our status quo assumption, which is always that there is not going to be an impact. The alternative is that it is altering the temperature of water. So because we failed to reject the null hypothesis, we would state that there was not a significant difference in the temperature of water prior to the application of the chemical as compared to temperature of water subsequent to the application of the chemical. P equals 0.06. And finally, we come to the paired samples Wilcoxon test. We're again working with the example of a watch manufacturer. A watch manufacturer believes that by changing to a new battery supplier, that the watches that are shipped, which include an initial battery, will maintain longer lifespan. To test this theory, 12 watches are tested for duration of lifespan with the original battery. The same 12 watches are then retested for duration with the new battery. So it's the same watch in each instance. Watch 1, watch 2, watch 3, watch 4, and it's paired sample, old battery, new battery. And we want to conclude that the new battery increases the duration of lifespan for the manufactured watches. Is there a significant increase in the lifespan of the watches with the new battery versus the old battery? Assumed alpha value of 0.05. And as you can see, each one of these examples heavily resembles the t-test equivalent. So we go to statistics, non-parametric tests, paired Wilcoxon test. We're going to select the new watch first and then the original watch. So this is the application versus the original non-application. So if you find yourself in a similar situation, this is how you would structure it. It's odd because you have to do like a vice versa where it's new versus old versus new. So make sure you remember to do this when using RCommander. You then have to click the Options tab here. Whether it's two-tailed, left-tailed, or right-tailed, in this case, we're looking at right-tailed because we're looking for a significant increase. Type of test is going to remain default. Click OK. Here is our output, and here is the data set, again, in CSV form. If you wanted to recreate it yourself from this particular slide, just copy these values and then import the data into RCommander. So we have new watch and original watch. P-value is 0.0170, 0.09. That would round to 0.02, which is less than our alpha value of 0.05. Because it's less than our alpha value, we reject the null hypothesis because the P was low, the null must go. The null hypothesis was that the new battery does not increase the duration of lifespan because it's a status quo assumption. We're always assuming with application that nothing is going to occur outside of the ordinary. This is the case for t-tests and their non-parametric equivalents. As far as the alternative hypothesis is concerned, we're going to say the battery does increase the duration of lifespan. So because we rejected the null hypothesis, the new battery does increase the duration of lifespan for the manufactured watches, or at least that is what our results would indicate. So we would state that there was a significant increase in the duration of watches which contained the new battery as compared to the lifespan of watches which contained the initial battery, P equals 0.02. So that is it for this particular lecture. I hope I wasn't too hard on non-parametric alternatives, but really they're difficult for readers to interpret, and you should really understand, even more so than what we covered in this slide, how they function if anyone has a question for you as it relates to your results, how the ranks actually work. So with that, I wish you all the best in your classes with your thesis or in general. Thank you for chiming in or tuning in for that matter and watching until the end. Hope you have a wonderful rest of the day and best of luck to you. Take care.